Good afternoon. Any questions? Any comments? Okay, if not, I'll start with the material. Okay. So I want to tell you about the uncertainty principle. So you may have noticed we didn't talk much about uncertainty principle. Generally, the attitude is like we have this wave mechanics and we have the rules. We just calculate the variance of x and we calculate the variance of p, and as a miracle we see them to be like bigger than some lower bound. And I think you have already done this many times in like modern physics and in more elementary courses. That's why I didn't press too much on it. But now I want to present it in a complete and formal way, following the textbook, I think, which is pretty good. And the key idea is like we have observables, right? We have the generalized statistical interpretation. We make observations by diagonalizing observables and finding their eigenvalues. And their eigenvalues are results of observation. And their eigenvectors are probability to observe a certain eigenvalue. Right? That's the generalized generalized statistical interpretation. And if we have two commuting observables, like we talked at length last time, they can be observed simultaneously. Or in the mathematical language, two commuting matrices can be diagonalized simultaneously. And the question is, what happens if they don't commute? If they don't commute, they cannot be diagonalized simultaneously. They cannot be observed simultaneously, or observation of one distorts the other, or there is an uncertainty between these two observables. And that's going to be the key about today's lecture. Good? First, let me introduce a little bit of machinery that we need to use. It's so-called Schwarz inequality. Suppose I have two vectors. One is like that, another one is like that. So this is A and B. And there is like some theta between them, theta. And we know the cosine theorem, right? It is like if you calculate A dot B, it is magnitude of A. I'm going to write it without, maybe I can write it just for this one. Magnitude of B times cosine theta, the angle between these two. Now if I take the square of both sides, I'm going to have A squared, B squared, cosine squared theta, right? And this is going to be, right, I take the square of this. This is A dot B squared. Therefore, if I look at this object, A dot B squared, because cosine is always something, cosine squared is always something less than 1, this is going to be less than or equal to A squared B squared. Okay, so this is the dot product in the linear algebra. This is the norm, like, right? A square is A dot A, and this is what we call Schwarz inequality, right? In the case of quantum mechanics, we can write it like for two abstract vectors. Dot product is F G, and if you take the square, it is going to be less than F F and GG. Okay? So that's all we need. So this is linear algebra. So this is in quantum mechanics, and they are valid. And if you have the each for like a formal proof, if you are that kind of person, you can look at problem A5 in textbook, in the appendix. But I don't need that, that's all I need. Now, suppose I have an observable A, and let little a be the expectation value of this observable. Okay? And now we now know A is a number, right? Because expectation value is a number, and numbers just go around. They don't have to be, they commute with everything. Then I want to define variance in A, which is square. Right? This is defined for a state. Let me use psi for this state. This is my state. And variance, okay, this is an operator. Operator minus mean square acting on psi. If you want, sometimes we don't put the get here like that. But since A is an observable, it has to be Hermitian, and little a is real, then A minus A is also Hermitian. So I can take one of the powers from here and put it there. So what I mean is, so I have this big bra, A minus A, acting on psi, close it, A minus A, acting on psi. Good? So I just took one and put it there, and I used observables being Hermitian. And I call this piece a Neve ket, let me call it F. Therefore, this thing is going to be F inner product. Okay. Now we can think about a second observable. Let's say observable B, and it is also going to have exactly the same thing. So expectation value is B, and if I define a ket G as B minus B acting on the same state psi, then variance of B is going to be sigma B squared is going to be G. Good? Yes?
Is there any difference between actually B operator minus B is in the ket or not? Is the difference here?
Like whether here or there?
No, the down.
This one?
Yeah. If
So,
B operator minus B is outside of ket.
I mean, yeah, I think for the moment, no. Like if you are really formal, mathematically oriented person, there's like a very tiny difference. I don't even care. Okay? Typically, I write it inside to make it compact and to define like a ket like this. If you like it, you can put it outside. But then the problem is when it is acting on the bra, right? In the bra, it is like, am I supposed to write it here? It's a little bit like ugly in the bra case. But for the ket case, whether you write it here or there, I think it doesn't matter. Good? So now that's all we need. What I want to do is now I want to use Schwarz inequality with these F and G. So what we did is F times G. I think here you can see this is supposed to be bigger than or equal to Fg squared. Now I want to think about this Fg. Let's manipulate this Fg a little bit. Fg is equal to I have f is a minus a ectagon psi, and g is b minus b ectagon psi. And I can take this from here to there, and I can write it like this: psi a minus a, b minus b. Okay, these are operators, but I'll forget. We know uppercase is operator anyways. So this is psi. Because it's formation, it came like itself. And this is going to be what? So this piece. So a b minus b a minus a b minus a b. And if I open this up, so this is last one is plus. Yes, thank you. So this is plus. So this is going to be expectation value of AB minus, so B is a number, just comes out, expectation value of A minus A expectation value of B, and this is just a number, and psi is going to be AB. Good. But we said expectation value of A is, okay, let me do it in 2 steps. So this one is A, this one is B. So one of them is going to cancel, and the result is going to be AB expectation value minus AB. And in the case of GF, I just need to put wherever I see A, I need to put B. Wherever I see B, I need to put A. Right now, I'm going to calculate G inner product with F, and this is going to be, I don't need to do the same calculation, right? I already did it. BA, and for AB, BA, they are the same. These are numbers, so there is no difference. Now you can see this FG and GF, they are like complex conjugates of each other. Let's write this. So FG minus, let me look at this, GF, right? If this is Z, this is complex conjugate Z star. And from here we know, right, we just calculated, FG is AB, and there's like a constant AB, and GF is BA, there's like a constant, and that difference, all I need to do is this, AB minus BA, and the constants cancelled, and this thing is equal to expectation value of A commutator with B. Okay, now let's put this back in. Okay, let me do one more line. So this is what I want to do. Like I want to calculate F, and this is G, and I know this is bigger than or equal to F, G, absolute value squared. And so this thing, so this entire thing is something like F G times G F. Like I said, if this is Z, this is Z star, and this is absolute value of Z squared. And we know what this is. This is real part of Z squared plus imaginary part of Z squared. And this is positive, and this entire thing is also going to be bigger than imaginary part of Z, right? Squared. And what is imaginary part of any number? Imaginary part is, okay, let me write it here. z is equal to z minus z star divided by 2i. But we just calculated z minus z star, right? Z minus z star is commutator of a, b. And this immediately tells me f g is bigger than or equal to 1 over 2i commutator of a with b squared. Okay. Now, what was ff and gg? Ff we just calculated, right? Here, ff is variance in A, and gg is variance in B. Therefore, what we had is, and I also want to take the square root, sigma A times sigma B, these are positive quantities, should be bigger than or equal to 1 over 2i A commutator with B. Good. Any questions? If you want, we know this is going to be positive, but just to make sure, sometimes you can also put absolute value here. So this is what we call generalized uncertainty principle between any operators A and B. Right? And now we see the importance of commutator, right? In the previous course, we said if A and B commutes, they can be simultaneously diagonalized and observed, and measurement of one has no influence on the measurement of the other. If this is not the case, if A and B commutator is non-zero, you immediately have an uncertainty between A and B, right? In the basis of A, B is fuzzy, or if A is sharp, B is fuzzy, or if B is sharp, A is fuzzy. Okay? Any questions? So that's pretty much it. Now I want to show you the meaning of this within a little bit more practical applications. Okay? So let's first note a couple of observations. First, so if A is a dagger, which is the case, right? These are observables, and B is equal to B dagger, they are both Hermitian, then A comma B, which is equal to AB minus BA, and if I take the Hermitian conjugate of this, so this is AB Hermitian conjugate, so we are going to have B dagger A dagger and A dagger B dagger, right? Because any operator O1, O2, when you take the Hermitian conjugate, you get O2 Hermitian conjugate times O1 Hermitian conjugate. We show this. But A is Hermitian, B is Hermitian, so I can just erase this. But this is what? This is minus A commutator with B, right? So the commutator of two Hermitian operators comes with like a minus sign, right? When you take the Hermitian conjugate, that's what we call anti-Hermitian. So this is the first thing. Second, suppose I have some anti-Hermitian operator, O is equal to minus O dagger. Then the expectation value of O is defined by psi O psi, right? And I can always carry this around. So this is going to be O dagger psi psi. But this piece is minus O, right? Is that clear? And from here, I see this is going to be minus O complex conjugate. And an object equal to minus of its conjugate is purely imaginary. Right? If I have x plus iy, and if I take the Hermitian complex conjugate, it's x minus iy. And if this is equal to minus of this, real part is 0, and it's purely imaginary. Then lastly, so in this expectation value, 1 over 2i a b is real, right? Because this is pure imaginary, divided by like an imaginary number is going to be real. So therefore here we are going to have like a positive quantity. Let's think about a practical example. So here's the most relevant example. So let's say A is X and B is P. And we need to look at commutation of A with B, X, P. And we know how to do this, right? This is going to be acting on NF, and this is going to be XP minus PX acting on F. And here, this P is minus I H bar del X. So this P can act on here, or it can act on here. So this is going to give us XP minus minus is plus I H bar minus XP F. Cancel these. From here we find commutation of X with P is IH bar. Now if we calculate sigma P, sigma X is bigger than or equal to expectation value of 1 over 2i. Commutator of X and P is IH bar. And this is equal to h bar over 2. Good. So there, just a little note, there are different measures of uncertainty. Typically, for delta P and delta X, we can use the variance. But if we have time, we are going to see, for example, in the energy time uncertainty, we can use other measures for delta X than delta P. There are some problems we have to be careful. I think you will never see it unless you are a specialist working in some weird system. But some problems you may not be able to define variance as the delta X, delta P. But here it's not the case, so let me write it. Delta X, delta P is bigger than or equal to h bar over 2. So that's usual Heisenberg uncertainty, right? Yes.
You define delta X and variance, right?
Yes, these are both. This is the variance in X, this is the variance in P. And that deviation is the square root of variance, right? I got mixed up sometimes. Yes, if you are careful like that, correct. Yes. I'm a little bit less careful. Sorry about that. Any questions? So let me let me try to do one more calculation and we can take a break after that. So let's think about minimum uncertainty . What's that? Oh yes, let me write this minimum uncertainty wave packet. Okay. So let's consider when we saturate the uncertainty bound. What is the minimum uncertainty we can achieve? And what is the corresponding wave function? So let's first write how we derived uncertainty and see when we push to the bound. So we had Schwarz inequality, F, G, G. We said this is going to be bigger than or equal to F, G, squared. And we said this object is going to have real and imaginary parts, right? Z star Z is real Z squared plus imaginary Z squared. And this should be bigger than or equal to its imaginary part, imaginary Z squared. So there are two inequalities. First, this inequality is going to be equality. So this one is going to be, let me call this condition 1, is going to be equality if F times G is equal to F G squared, right? And for this to happen, you can kind of see, right? If F is some constant times G, then this is this constant and this constant, right? This immediately follows. I think I called it the other way. Let me call it, I think it doesn't matter. G is equal to some constant times F. And the second one, let me call this the condition 2. This one is going to be equality if real part of F G is equal to 0. So if I have both of these conditions satisfied, this bigger than or equal to is going to be equal to. And that's the minimum uncertainty I can achieve. But what is this real? This real, let me write it, real Z is equal to F G plus its complex conjugate GF. And from condition 1, we call G is some C times F, then this is going to be F CF plus CF F. We know C is a number, so here it's going to come out like C times FF. Here it's in the bra part, so it's going to be C star plus C star F F. Yes? Oh yes, I think yes, I think it is, let me write it like this, 2 times real part is this. And then we require C times C star F F. And what did we say for the condition? Our condition requires this to be 0. But we know F is not 0, then C is going to be minus C star. The condition we found is G is equal to some C times F, and C is minus its complex conjugate. That means C is purely imaginary. Let's call it C is equal to some I times beta, and beta is real. So what we found, let me write and let's clean up. We found G is equal to I beta, beta is real. Then this is my minimum uncertainty. Let's now write what these things were. So G was B minus B times psi. and F is A minus A times psi. So let's see what this gives us for our practical example. I want to choose A to be X and B to be P. And let me also define expectation value of X. I don't want to keep writing this, so I will write X naught, and expectation value of P, I'm going to write it P naught. So this is so this is B is minus I H bar D dx minus expectation value of B is P naught, acting on psi is equal to I beta X minus X naught times psi. Right? Now, this is like a first order differential equation, right? We solved it many times, but there's like an X, but there's no problem. You can ponder about that. Let me write you the solution. If you solve this, psi is going to be some overall normalization constant times e to the minus beta over 2 h bar x minus x naught squared plus I over h bar p naught times x. Okay. So this is our beloved Gaussian, and that's why we have the minimum uncertainty if you have a Gaussian. Like in the case of harmonic oscillator, right? The ground state of harmonic oscillator, which had energy h bar omega over 2, is the minimum possible uncertainty you can achieve.